All right, welcome back to The Explainer. Today, we're diving into what I think is the ultimate electrical detective story, unraveling a highly critical battery software anomaly known as P057F. Now, this isn't just some standard little glitch. We're talking about a complete breakdown in communication between the physical chemistry of the battery and the digital algorithms trying to manage it. If you've ever wondered exactly how modern EVs keep track of their invisible energy and what happens when that tracking completely derails, well, you're in the right place. Let's get started. Picture this. You're cruising down the highway, right? Range looks good, everything is fine, and then suddenly, out of nowhere, your battery gauge just nosedives from 40% straight down to 15% in the blink of an eye. I mean, what on earth is happening inside the machine to cause a terrifying drop like that? Spoiler alert, it's not a sudden leak of energy. It is a massive crisis of confidence happening deep within the vehicle's brain. To unpack this, we're going to follow a precise roadmap. We'll hit the P057F root cause analysis, jump into hardware and software co-diagnosis, look at DFMEA, design prevention, PFMEA process control, and wrap it up with DVP&R mass production verification. Let's get into it. All right, phase 1, P057F root cause analysis. We have to understand the fundamental breakdown before we can fix it. So the core of this P057F fault code, it's basically a severe digital hallucination. The battery management system, the BMS, calculates what it thinks the charge level is. That's your software state of charge. But suddenly, that calculation completely detaches from reality. It diverges heavily from the battery's true chemical state of charge. Simply put, the software just loses its mind and stops reflecting what's actually happening in the cells. So what actually triggers this digital hallucination? There are a couple of sneaky physical culprits, what we can call electrochemical lesions. First up is long-term shallow charging. Say you only ever charge your car between 40 and 60%. The battery never gets a long enough continuous rest to figure out its absolute open circuit voltage anchor, its OCV. Without that absolute anchor, the system is flying blind. Then you've got sensor zero drift, and these tiny little phantom ghost loads. We're talking microcurrents, less than a single amp, slipping past the sensors when the car is totally shut off. Over time, those tiny uncounted electrons pile up, causing massive accumulated Coulomb counting drift, which engineers refer to as quantization error. Now, this gets incredibly chaotic if you're dealing with LFP, or lithium iron phosphate, batteries. LFP batteries have a totally flat voltage curve, right in the middle section, roughly between 20 and 80% charge. Because the voltage barely moves at all, the software really struggles to figure out where it's at. If the algorithm suddenly decides it needs to force a calibration right in the middle of that extreme flat section because of some tiny error, oh boy, it totally overreacts. You get these wild, violent oscillations in the extended Kalman filter equations. The software just straight up panics. Moving right along to phase 2, hardware and software co-diagnosis. Let's see how the system spots this anomaly in real time. Well, the BMS uses this brilliant dual estimator system to catch the hallucination. Think of it like having two competing accountants working on the exact same ledger. Your L1 accountant is using an adaptive extended Kalman filter, the AEKF. It's super advanced, constantly predicting the battery's future using complex dynamic models. But your L2 accountant? That's traditional Coulomb counting. It strictly tracks the past by tallying up every single electron that goes in and out using fixed voltage limits. The system is just constantly comparing their math, and the magic number here is 15%. The software is constantly watching for a gap between our two accountants. The exact second their disagreement hits that hard 15% limit, boom, the system officially declares a P057F crisis. It recognizes the math is completely broken and it needs to step in right now. The moment that trust is gone, a rapid fail-safe cascade kicks in, instantly. Step 1, abandon the bad Coulomb counting math entirely and downgrade to a safer voltage-based estimation. Step 2, aggressively shrink the battery's working window. It locks it strictly between 30 and 70%, so you don't get any extreme overcharging or deep discharging. And step 3, which is honestly the most important for whoever's driving, it talks to the vehicle control unit to gracefully limit motor torque. By reconstructing the state of power map, it smoothly reduces the output so the driver doesn't feel some sudden, terrifying jerk on the highway. All right, on to the vaccine. Phase 3, DFMEA Key Design Prevention, where we see how engineers build fixes straight into the software. When engineers run their DFMEA risk assessments, this P057F failure gets a brutal severity rating of 7. And it makes sense, right? An unexpected loss of power, or your dash suddenly flashing 0 miles of range while you're driving in traffic, that's completely unacceptable for reliability and safety. So to fight back, they load the software up with specific design vaccines. First, that AKFK algorithm is upgraded, so it dynamically updates its internal noise matrices based on things like temperature and battery age. Next, they use inflection calibration. It looks for specific voltage peaks and valleys while you drive to mathematically cap how far the estimation can wander off. But honestly, the smartest trick is the confidence level index. If the software realizes, hey, my confidence is dropping because this driver has been shallow charging for weeks, it actually steps in. It'll restrict pure EV modes to force the car to take a break and quietly auto-calibrate its OCV anchors while it's parked. Let's leave the code for a second and hit the factory floor. Phase 4, PFMEA Key Process Control Measures, securing the physical hardware. Because tiny hardware quirks can trigger this whole software nightmare, random sampling on the assembly line just doesn't cut it. 100% of these units have to go through rigorous, multi-temperature, end-of-line calibration. They test everything from massive acceleration peaks right down to tiny sleep currents, all to absolutely kill any hardware zero drift before that car is ever sold to a customer. Factories actually use really strict physical defenses for this. They use incredibly precise servo-tightening systems with specific fixtures for the shunts. And that's to stop even microscopic mechanical bending. Because if a shunt bends even a tiny bit, its resistance shifts by microohms. That ruins the math years down the road. They also run a 100% dataset checksum when flashing the software. This perfectly matches the specific OCV and SOC parameters to the exact chemistry of the physical battery installed in the car. You absolutely cannot have a mismatched brain and body here. And that brings us to Phase 5, DVP&R, Mass Production Verification, the ultimate stress test. Before mass production gets the green light, the stress tests they run are, honestly, they're intense. They take aged batteries, packs that already have over 800 cycles on them, and just torture them with a WLTC dynamic test loop at 25 degrees Celsius. To pass, the error margin has to stay strictly within plus or minus 3.0%. But the phantom load test is wild. They intentionally inject a sneaky 500 milliamp leak into a sleeping car for 72 straight hours. The passing grade? Once that car wakes up, it has exactly 500 milliseconds to spot the drift and auto-calibrate it down to a tiny 50 milliamp residual. It all builds up to this, the ticking clock test. Engineers will manually inject a massive 20% SOC calculation error right while the vehicle is at full throttle. The system then has a 15-second window to spot the P057F fault and trigger the malfunction indicator lamp, and that little turtle light on the dash. Then, within 2 seconds of that confirmation, it has to shrink the battery window to 30 to 70% and smoothly derate power to about 30 to 50%. A safe, graceful limp-home mode without causing an accident. But listen, the ultimate fail-safe here is pretty stark. If the software permanently loses trust in the battery math, it permanently bans DC fast charging. Just a total lockout. Because if the system is blind to the real state of charge, allowing a massive flood of fast charging current is a guaranteed recipe for overcharging and catastrophic thermal runaway. Safety absolutely has to override convenience every single time. So we've seen the incredible lengths engineers go to just to catch and isolate a sudden SOC calculation anomaly. But it really leaves you with a fascinating question to chew on. If the system uses this exact dual estimator logic to protect your daily charge, how does the same architecture dynamically decouple and predict the total health, the SOH, and the ultimate death of the battery over its entire 10-year lifespan? Well, that's exactly what we'll be diving into next time. Thanks for hanging out with me on today's Explainer, and I'll catch you in the next one.